Good afternoon, sir. My name is Keshav Sharma, and today we are going to dive into the core. One second. We are going to dive into the core operating system performance by exploring CPU scheduling algorithms. We'll look at how OS decides which task to get processed and when to maximize efficiency. So, yeah. So to start things, what exactly is CPU scheduling? In modern multi-programming systems, you have many processors and many processes running simultaneously, running at once. Uh, CPU scheduling is the mechanism that determines which process gets to use the CPU while others are waiting. The dispatcher is the specific module that hands over controls, making sure the CPU is never sitting idle to maximize its efficiency. Uh, Third slide, it's about key scheduling criteria. So, when we design or choose a scheduling algorithm, we evaluate it based on few key characteristics, like throughput, like how many processes we can finish in a given time, or the turnaround time. uh, it is how many processes we sorry, it is how long a single process takes to finish, from start to the end. And the last, waiting time, it is how long a process spends sitting idle in the queue. Ideally we want to maximize throughput, we want to maximize the throughput while minimizing turnaround time and waiting time. Next one. So let's look at the simplest algorithm, which is first come first serve, FCFS. It works exactly like a line at a grocery store. First, the first process to arrive gets CPU time until it's done. While it is incredibly simple and fair in theory, it suffers from a convoy effect. It means if one massive task gets in the front, मतलब एक टास्क अगर शुरू हो गया तो वो ख़त्म होके ही हटेगा, विच मीन्स इट किल्स एफिशिएंसी। बहुत टाइम लग जाएगा, बाकी सारे जो प्रोसेस होंगे वो आइडल बैठे रहेंगे उस टाइम तक, तो सीपीयू का एफिशिएंसी भी कुछ नहीं होगा। Uh, so the next slide, it is to solve the convoy effect. We have the shortest job first, SJF. This algorithm looks at the queue at and gives the CPU the processes that needs the least amount of time to be finished mathematically. This is the optimal way to minimize average waiting time. The tricky part, however, is that the OS has to predict how much time a process will actually need based on its past behavior. वो सबसे मुश्किल पार्ट है, बाकी इसके बाद भी हमारे पास और एल्गोरिदम्स हैं, जैसे कि प्रायोरिटी शेड्यूलिंग। हियर every process is given a priority rank, usually an integer 1, 2, 0. The CPU always goes to the highest priority task. The main danger here is starvation, मतलब जिसके पास lowest priority होगी वो आइडल बैठा रहेगा, वो कंप्लीट ही नहीं हो पाएगा और उससे स्टार्वेशन हो सकती है। उसके बाद हम ओ एस फिक्स दिस यूजिंग एजिंग, विच ग्रेजुअली इंक्रीजेज द प्रोसेस प्रायोरिटी द लॉन्गर इट वेट्स। लाइक एजिंग मतलब जितनी देर किसी प्रोसेस ने स्टार्व किया या वेट किया उतनी उसकी प्रायोरिटी अप कर देते हैं ताकि उसकी नेक्स्ट चांस जल्दी आए। Then the last one is RR, round robin method. It is designed specifically for interactive time sharing systems like the computer we are using. Uh, it gives every process a small strict time limit called a quantum. Um, Once the process uses up its quantum, it gets paused and moved to the back of the line. It ensures every application remains responsive. यही इसका मेन मोटिव है। एंड द लास्ट थिंग इज कंपैरिजन। हियर this is a quick summary matrix of all the algorithms. FCFS is simple but it is slow. SJF is optimal but hard to predict. Priority scheduling is great for critical tasks, but it risks starvation. Round robin is excellent for interactive systems, provided the time quantum is balanced correctly. Last is performance targets. Uh, like, what are the actual performance target OS is aiming for? We want to keep the CPU busy, but not completely overloaded. A healthy system typically a healthy system typically targets between 40% utilization when idle up to 90% under heavy load. Pushing past 90% usually means your system is starting to freeze or lag. The last slide, the last second slide is execution cycle distribution. It is important to understand what a process is actually doing. A process isn't just crunching number the whole time. It alternates between CPU burst and IO burst. Like, CPU burst is main task, IO burst is reading a file, waiting for a click and all. A great scheduler overlaps these, so while one app is waiting on a hard drive, another is using CPU. The last slide is real world implementation. So, to bring this into real world, modern OS are highly advanced version of these concepts. Linux Linux uses completely fair scheduler, which relies on complex tree data structures. Windows Windows uses the preemptive priority system with 32 different levels. Mac OS uses a multi-level queue that constantly adjusts priority based on what the user is interacting with. So with this, the CPU scheduling algorithms are done. Thank you.